All right. So just to make a quick announcement in case that you haven't seen it, the previous lectures are already on the YouTube playlist. All right. So you can get the link to the playlist by looking at the announcement in the Google Classroom. Okay. Along with, I think I posted the notes that we sort of like the written notes that we did in class as well on the material section there. So just check them out. Already. Okay, guys, take a look at this problem and see how can we deal with this. All right, so this one sort of like try to bring you guys back a little bit toward mechanical stuff, but we sort of like attach the involvement with the temperature, with the heat and all the stuff along with it. So I just to have you guys have a feeling of what is supposed to going in a real world situation, that when you sort of like take the Newtonian physics and then sort of like add the thermodynamics on top. Sound a little bit, right? Not much, just about heat. So it's not like total thermodynamic stuff, but at least you see some connection in this example right here. Okay, let's take a look. So you have a 3-gram lead bullet at 30 degrees Celsius and is fired at the speed of 240 meters per second. All right, so sort of like this is the kind of feeling that you got before. Now you have the speed, you have the stuff. Now you fire this bullet into a large block of ice, which is standing at 0 degrees Celsius, in which it becomes embedded. All right, perfect. So it's stuck in there. What quantity of ice melts? That's the question. All right. So that's kind of sort of like a good applications of the bridging between just the mechanics and thermodynamics. Okay. All right. So let's sort of draw some picture here. All right, so you have a large block of ice waiting, okay, and then you fire a bullet into it. Now the information that you have is, of course, is a 3-gram. That always you can turn this into kilogram SI system. That's fine. Okay, and now see the difference, just like I mentioned last week. Before, you didn't care about the temperature of the bullet, right? It's probably just had this kind of problem in the like momentum calculation. You had this thing in like a maybe conservation of momentum, and you want to know like what is the energy lost during this firing of these bullets, or maybe if the ice allowed to move a little bit. So you probably want to know like how the bullet that's embedded in the ice block is going to move after the hit or something like that. But this is not the case. The case is we assume that this lead is going to stuck in this ice. And at first, it started with 30 degrees Celsius temperature. Okay, so it has an initial temperature of the bullet. All right, once it hits the block, it's stuck in there. Okay, and the block, it's big. They say it is like a sort of, let's assume that it's big enough. So the block stays at 0 degrees Celsius at all time. Okay. All right, so what can we do? Of course, once you fire this in, the thing is, there must be a heat going on. The reason is heat because at first, there is the initial energy of the bullet. Does that make sense now?
Okay.
Yeah. So what you are looking at right now is like, okay, then you have an initial energy, but then afterward, that energy is gone because once the bullet stopped moving, the kinetic energy disappears. So I can even make this one sort of like explicitly say this is the kinetic energy, 1/2 mv squared. That's you starting with. But at the end, it's gone. So let me put this like a final energy of the bullet is 0. So I can take this one as an initial. Okay, cool, guys. So this is what it is. Okay, so this is the mechanical portion of your analysis. So you say that, okay, the kinetic energy disappeared. But not only that, the temperature of the bullet, you start with 30 degrees Celsius. And at the end, that temperature changed to 0. So that is the change of the temperature due to, I mean, you have the thermal contact between the bullet and ice. So there is a heat leaks due to the thermal effect on top of that. Does that make sense now? Okay, so what I'm trying to say is, so what you want is you want to know how much ice melts. So the melting of the ice, we know that we use the land heat a fusion calculation. So we want to know the amount of mass of ice melt. So we say that quantity, let's assume that's M, times the latent heat of fusion, that you can look it up from the table. So far so good. So this is going to allow you to calculate how much ice has melted during this process. But then you have to equate this to the amount of energy that's transferred to the ice. Okay, so first thing first, it's going to be the heat that coming from the hot part, which is the lead bullets. So you're going to have MC delta T. This is from the bullet. Okay, let me put subscript on there just to be clear. So let me put the subscript B, that's the mass of the bullet, C of the lead, and the delta T of that bullet. Does that make sense? Okay, plus that will be another chunk of energy coming from the loss of the kinetic energy that we just discussed right here. So that disappearing of the 1/2 mv squared initially is going to get transferred to the ice. So it's going to be 1/2 mv squared right here. And that's the mass of the bullets times the velocity of the bullets initially. Sounds good, guys? Okay, all right. So that's what it is. So that's it. So the rest, you can just calculate M by taking the mass of the bullet, 3 times 10 to the negative 3 kilograms. C of the bullet is the C of the lead. You can look it up. Delta T of the bullet, temperature is reducing. Now, the way that I'm doing right now, if you notice, I'm just taking the magnitude of this one and compare. Does that make sense? So I'm just trying to remind you what we did last week as well. So you know that actually, if you really calculate just a pure delta T of the bullet, you're going to get a negative number because the temperature of the bullet is reduced. Does that make sense? All right. So if you stuck with the actual definition of the delta, then you're going to see that the change of the temperature of the bullet is going to give you a negative number, because that negative means the energy, which is the heat, actually it's gets leaked out, or it's actually transferred out from the bullet to, in this case, to the ice. Okay, so actually what I'm doing right here is I know in my heart that, hey, this is the amount of energy that the ice block is receiving. So actually I can just take the positive number and put it in here. So I know that the change from 30 degrees Celsius to 0 degree, the change is 30. Does that make sense, guys? So I just take the absolute value. I just take the chunk of the energy that gets transferred into this equation. Okay, cool. All right, keep going. Plus, now the initial and kinetic energy is just 1/2 the mass of the bullet again, and times the speed of the bullet square. And that's it, guys. You can calculate everything here and divide it by the L of that latent heat of fusion, and then you're done. You get M, the mass of the ice that melts. Okay, done.
Okay.
Cool. Okay, so I'm not sure am I confusing you in terms of the sign or anything, but at least this kind of problems just sort of give you the connections between the pure mechanics that you did before, plus now we have the thermal aspect in our analysis. All right, so this is one just like give you the combination of the two in one problem. Okay, so I think this is like a good exercise for you to just have, you know, some problem that allow you to think. Okay, there's a question comes in. Why is kinetic energy and energy Q interchangeable? Well, can you explain a little bit more? Okay, there's a question coming in from one of your colleagues here. Let me have a good answer for that. What does it mean? Why is energy Q interchangeable? Okay, I'm not so sure. Can you maybe explain a little bit more about interchangeable? What does it mean by interchangeable? So I assume that you mean that why we can mix between the kinetic energy and the heat. Is that right? Is that what you're saying? Okay, all right. So I think this is what it is. Okay, that's a good question. So I'm not sure when when I explain what I just did, I don't know, does that make sense to you or not? But if you look at this term, right, you have to know that what I'm doing right now is the change of the energy. It's a change of the energy. So that means when I say the change, mean initially the lead has this much of the energy. Later, it has 0. So if to be, I mean, if I want to be more explicit, I have to say that this one sort of embed this kind of thing in here. Does that make sense? Is that better? So 1/2 mv squared that you're seeing here is not, I'm not like just take the kinetic energy and stuck into the ml expression. No, it's actually, it's the change already. Okay, it's the change of the kinetic energy that contributes to the energy that is going to melt the ice. All right, so everything that we are doing over here, we still stick with the, it's the original concepts of heat. Heat, Q, heat is always the energy transfer. Okay.
Okay.
All right. So it's always the energy transfer. So every time that you thinking of the word transfers, so you assume that there must be some change. That it might imply some change, even though the change could be 0, but at least you must be considering 2 scenarios, 2 state, 2 situation, 2 whatever things before, after, initial, final, on and on. Okay, so you're always looking at some differences between 2 situations, 2 states. Okay, does that make sense? All right, so I think that's a good question. So in conclusion, what I'm saying is you have to be able to distinguish between the energy, which is the amount that sort of like contained in a body, that is energy. Like you have your own kinetic energy, you can have your own potential energy. That's in you, that's inside your body. But then when you do something, when there are some changes going on, there is an exchange. The reason that the only way that you can change the energy of your body, there must be some interaction with some other things. So there must be some sort of like a transfer going on. And that transfer is either in terms of heat or in terms of work that you did before. Okay, does that, I don't know, does that help? Yes, I would say yes, yes, yes. Anything. So this one works universally, right? So it doesn't have to be just this. It could work in electrodynamics. It could be in waves, in anything, right? The concept of energy transfer is gonna fall down into either in terms of thermal or purely mechanics. All right. And once you combine them all, that's thermodynamics right here, guys.
Okay.
So seems like thermodynamics is huge, right? Because you put the sort of like a thermal aspect of this one is like a cherry on top. You just make things like now completely beautiful and all this stuff. Came from just pure Newtonian physics. Yes. Okay. So I think you got it. Yeah, correct. So just your friend just confirm that that's it is. That's what it is. Yeah, energy transfer. That's the key. Very good. All right. Any other questions, guys? Thank you for the question. All right. Okay. Good. All right. Keep going, guys. So we are going to look further now. It's going to be a lot more fun this week, I think, in comparison to last week. So I'm going to bring up the next handout. So it's going to be the handout number 2. All right. So I'm not so sure that we can finish this within the second week or not, but I should have changed this week 2 into like lecture number 2, handout number 2 or something like that. Okay. Now, today, I am going to eventually lead you to, right, the other half of the story. We talked about heat so much already, and we mentioned briefly about work. So I'm going to bring work into the picture now. Okay, that's it. And once you have that, we're going to bring back our sort of our old friends, energy. And now we're going to have a sort of like a specific name that we're going to mention to them in thermodynamics. We're going to call them internal energy. All right. So once we have that, today you're going to have a chance to see what it means by first law of thermodynamics. All right. So that's what we're going to do today. All right. And on Wednesday, we're going to look at some processes. That's where the fun sort of like begins right there. All right, guys, let's dive into this. So this is the part that, I mean, even though you look at this slide, it might look annoying a little bit because there's so many expressions going on and it looks like a little bit of differential and stuff, but the concept is simple. We will go back to work again. Work is force time displacement. Okay, everyone like, okay, John, this is no big deal.
Okay.
That's fine. But said, hey, we already agree that we don't want to deal with force anymore. It's too microscopic. It's like, okay, I don't want to deal with the microscopic parameters anymore. Let's move away from it. All right. And that's what we are going to do here. See, look at this. Now you have a movable piston that contains, there is a portion inside that contains a gas. All right. We said gas is perfect for our study here. So what you can do now, you can compress this piston down so the gas get compressed. So the volumes change. Okay. So there is a volume change going on here on the gas. So what you have over here is, if I'm asking you about, hey guys, how much work are you doing right now? So you're compressing it down. So you say, well, Ajahn, that's no big deal because you can see that the travel distance of this piston is, let's say, dy. So let's say like, a differential, you just press it just by a little bit. And then, so how much work are you doing? Well, Ajahn, that's easy. The work that is being done is just going to be F dy. You guys with me so far?
Okay.
Yeah, because now the force is down. The displacement is also down. So if you want to start from the beginning, it's going to be F dot the vector dy. Okay. Or better yet, if you want to express it in terms of the ijk, this is sort of like give you a little bit of the vector notation. Then it's going to be dy, sorry, dy along the negative j direction, if you like. So if you want to like put everything in the vector form, if you want, okay? So that's what it is. All right, it's fine. So far, so good. But what I'm doing over here is, well, Ajahn, I don't want to deal with the force anymore. Here, this is the change. Is there any other thing that we can do? Back in the fluid dynamics that you just did in the 101, you say, okay, if you don't want to deal with the force, but at least can you sort of figure out the area for me? Okay, Ajahn, I can figure out the cross-sectional area of this piston. So if that is the case, then we can refer to the pressure inside this container over here, because by definition, the pressure is force per unit area. So that means you can always express force as a product between the pressure and the area that that force is being acting on. Does that make sense now? Well, okay. So that means I can get rid of this F and turn this into the pressure multiplied by the cross-sectional area if I want to. And I know the direction is supposed to be somewhere like sort of upward and everything on and on. That is fine. Okay, so now I can move away from the force and put them in terms of the product between the pressure and the volume. But once I have that, then this is a nice thing about this one. Then now you can pair the cross-sectional area and the dy that you just saw before is just this volume right here that I'm highlighting yellow at this point. See that? Does that make sense? All right. So that means the cross-sectional area multiplied by the height, the A dy, actually that is the change in the volume. Perfect. So that's good. So that means I can wrap these two together. And let me call this the change of the volume. Is that cool? All right. And that's it, guys. So that means from now on, I can actually express the work done by the whatever force that you're acting on this gas is going to be the product between the pressure multiplied by the volume change, differential change of the volume. And now we get rid of the F altogether. Don't have to worry about the force anymore. Okay, cool. So far, so good. All right. But now here comes the problem a little bit. When I'm writing right here, okay, you don't worry, you don't have to worry about this, whatever the sign and the stuff that I'm trying to write here, because I think by looking at the argument that I'm about to explain, it seems to be a little bit better, I hope. Look at this one. When I look at this, the pressure that I'm trying to look at has an arrow pointing up, right now. But the force that I'm acting to the gas is actually pointing down. It's sort of opposite. Can you see that? So there are two directions over here. So the force that I just started out with, that is the force that somebody outside the gas is compressing the gas down. So I have to actually express this force to be external force. Okay, you guys with me now? Okay, is an external force acting on the gas. But the force that I'm referring to here, down here, it seems to be the force that the gas is actually acting on the wall. So this seems to be the force of the gas. So let me put the system here. That's the system. Okay, so there is a problem a little bit in terms of the sign. what I'm seeing over here is this. So every time that you would like to talk about the pressure, that means you want to talk about the force that sort of like initially being applied by the gas itself. That makes sense? And that is the bottom arrow over here. The gas is pushing the wall or the ceiling, whatever at this point. And that is trying to go against the whatever external force is being applied on. So if you use these two forces, of course, the work done will be in the opposite side. Okay. If the external force doing a positive work, so in this case, it means the piston is moving down. So that means the external force is doing a positive work. You guys with me? Yeah. Okay. However, if external force doing positive work, from the perspective of the system has a negative work. You guys with me? So this is the most confusing part at this point. But once you're done with this, then I think you're done. Okay. So that's why what I'm trying to say is, if you care about the external force, okay, whenever the external force doing a positive work, it means the system doing a negative work. Okay, one more time. All right, I'll explain in the opposite sense. Let's say you're doing a reverse situation. Let's say if you have a gas and the gas is expanding. So that means the gas is pushing up the piston. So the gas doing a positive work. Okay, you guys with me? All right. So if this gas pushing up, so the gas, which is now we call system, doing a positive work. Okay. But then if you look from the perspective of the external force, the external force will do a negative work because it's being pushed back. Okay. So in conclusion, external and system always have a positive sign of work. Okay, that's the first key thing. Okay, that's done. All right, there's always opposites. All right. Now, when you look at this, when say, well, Ajahn, if we focusing on the system, because we are going to care more about the system at this point. So if we sort of stick with our system, so what you can see is whenever the system is expanding, the gas is expanding, system doing a positive work. You guys with me? Okay. So it means the expansion imply or indicates the positive work done by the system. Okay. And that is going to give you a negative work done by the external force. And here comes the conclusion. Okay, one more time, slowly with me. Down here, that's what I'm trying to get to. The work done by the system, right here, can be calculated from the pressure multiplied by the volume change. Because we already agree, we don't need to worry about the force and the displacement anymore. We can do the product between the pressure and the volume change. So that means this expression will allow you to see if the volume change give you a positive direction change. So it means gas expands, okay? Then you're gonna get a positive work done by the system, okay? And automatically, if you care about what is going on from the perspective of external force, you're just gonna have the negative side popping in. Okay, guys? So in conclusion, this is the expression that we're going to use. It's right here. So the work done by the system, this is important, by the system is just the integration of the PdV. Or it's just pressure times your volume change, and then you just add them up. When you add them continuously, that turns into integration.
Okay.
And that's conclusion. Cool. I don't know, I'm talking too much about just the definition, but I think that's better for you to understand the difference between the work done by the system and the work done by the external force. Because I mean, all the textbook, they try to talk about these two things sort of like it depends on the flavor of the author. Some author prefer doing things externally first and then, you know, try to explain the system, and then some book talk about the system first and then trace back to the external, even though they both eventually is going to be the same once you understand what is going on. Okay, so let's, I mean, if you're still sort of unclear a little bit, that's all right. Let's move on a little bit and things will sort of get on top of each other. And then I hope you understand much better when you see more of this stuff. All right, but at least this gives you an introduction of, all right, John, we're going to be able to calculate work by do the P times the change of the volume. Here we go. Good thing about this is, all right, here we can write down the conclusion at this point. Work by the system is P times the change of the volume. I'm writing it down in terms of the integral, but that's all right. The good thing about this expression is this. If you remember from chemistry, it doesn't have to be chemistry, but physics, we are doing the same thing. You learn about the PV diagram. Sort of like ring any bells here? There's a reason for it, why you focus so much about the PV diagram. The reason of the PV diagram sort of very useful because of this. Look at this. If you take P to be the y-axis, V to be the x-axis, so actually this is like a y dx. What do you think?
Okay.
Let's welcome calculus here, shall we? So what you see over here is the integral of y dx, and that is just the area under the curve that this thing is explaining. With me? So that's nice. So that means if somehow you have a way to describe the change of the gas on the PV diagram, you can just look at the area underneath the curve. This will definitely tells you what is the work done by the system. Is that cool? I think this is very cool. Here we go. If you look at this, second one, all right, don't worry, John, I'm just gonna find the area under the curve, and that will give you my W. If it's a curve, I don't care. I just integrate finding the area under the curve, and I'm gonna get my W. Okay, cool. That's one thing that you have to be able to sort of like, okay, make the connection with. Second, if I'm asking you this, a simple question, guys, let's take a look at the figure A. If you start from here, initial point, and now you compress the gas along this line, come to this point, and then you increase the pressure without changing the volume, and then you end up here. Do you think the work done by the system supposed to be positive or negative? What do you think? Supposed to be positive or negative? Figure A, going from I to F, even though you know how to calculate the area under the curve, right? You know, right, it's just width times height, whatever. But what do you expect at the end? It's supposed to be get a positive or negative numbers here. Simple, guys. You start right here, big volume. You end here, smaller volume. So it's a contraction, right? It's a compression of the volume. So the work done by the system must be negative. You guys with me? It's a compression of the gas. So it means the gas get work done on something else outside compressing down the gas. So that's why from the perspective of the gas, I'm doing negative work. Okay?
Okay.
That's easy. That's super easy like that. Okay? Don't think too much. Over here. What about the figure B? Well, same scenario right here. You start from here. That's a big volume. You end here the same final volume. This is going to give you a negative work done anyway. All right? So we'll be more careful with the area under the curve. Here, you start right here, big volume. So these three figures start from the same initial volume, ends at the same final volume, which is smaller than the initial volume. They are all going to give you a negative work done, all three cases. So why I would like to talk about this? This is because here, this integral over here, or the area under the curve, is going to be very crucial at the end because you have to worry about the sign. So that's why you have to stick with the mathematics. Mathematics will take care of the final sign yourself. Okay. And this is sort of like sometimes things get confusing because you care about the area under the curve. And whenever we talk about area, you don't care about the sign, right? Because that area never go negative. But actually, that's just the magnitude of the work. But you have to figure out the sign because now work has direction. That's the gas doing the work or the gas being worked on. Okay, keep going, all right? It will get better and better over time. Here, let's give it a shot. So over here, the amount of heat flow and work done depends on the process. This is the good thing about seeing work. Every time that you want to start from A and you want to end at B. See, initial points the same, final points is the same. I mean, you get this all three cases sharing the same initial and final points on the PV diagram, correct? But the path that take the system from A to B, in this case, you see three paths, 1, 2, and 3. They all having different area under the curve. So that is the key things about work. It's path dependent. Okay, so work need to accompany by a graph, a curve, or whatever. I mean, you need to know how you bring the stuff from point 1 to point 2, from point A to point B, because it's path dependent. You cannot just say, hey, I'm moving my system from A to B, calculate the change in the work, or what is the work done from going from A to B. No, you cannot do that. Okay, you have to tell exactly how you bring your system from A to B for you to be able to calculate work done from A to B. All right, so that's, make sure that sort of you have this in the back of your mind. Okay, keep going. All right, so let's practice a little bit and see how things goes. You have an ideal gas undergoes a constant pressure expansion. Okay, very good. You have a constant pressure expansion. So what I sort of like ask you to think along with this is, think in your head in the PV diagram. Constant pressure means the process that you're looking at is going to be just a horizontal line right here. You guys with me? Okay. Its initial pressure is 1 atm. So let me mark on that, 1 atm. Its initial and final volume are given to be 2 and 4. So that means initial volume is 2, final volume over here is 4, and it's in the cubic meter units, which is nice. What is the work done by the gas? See that? Now you start from 2 to 4. Here, I have to add an arrow here. There, right there. The arrow is important because right now what you can see is the gas is expanding. And you should be able to expect in your head, Adan, I know the work done by the gas, I know it's going to be positive, at least. Right? I know that. Okay, but how much? Okay, let's do that. I'm going to start from the top. Work done by the system equal to the integral PdV. Let me start from the integral form over here just to practice you guys, familiar with the expression. But this one make things very easy because pressure is constant here. I can pull P out from the integral. Very nice. And I can put like initial volume here and the final volume there as a limit of integration here. So far so good. The integral of dV doesn't give you much. It's just going to be V. And then you just put the V initial and V final right there. And that is going to be P V final minus V initial. You guys with me now? Okay, not much. And this is exactly as we expect because P, that is just the height. V final minus V initial eventually will give you the length over here. So that's perfect. It's just the area under the curve. All right, so this one, no surprise.
Okay.
This one is good. However, this is the key that I told you about. The mathematic will take care of the sign by itself. See that? By this expression, it means that the work by the system is going to be P times V final minus V initial. And in this case, V final is bigger than the V initial. So that's okay. Let me plug in the number here. So it's going to be 1 atm. I can change the unit later. V final is 4. V initial is 2. See, the number is automatically positive. So the mathematic already take care of the final sign of the work done. All right, even though you expect since the beginning that you're going to get positive number, but this is the confirmation there. Cool. All right, and then I can convert atm into Pascal, and then let's say approximately 10 to the 5th on, and it's multiplied by positive 2. And the final unit is going to be in joule. So this one will give you positive work done right here, and you are done.
Okay.
Okay. Not bad. I would say not bad, not bad at this point. Okay, try again, shall we? Any questions so far? Okay, all right, get going. Okay, guys, try this. 3 mole is D a constant? Okay, there's a question here. Is D here? Is this a differential? Here we go. Yeah. Okay, this is the way that you write the integration operation. Okay, okay. All right. So D is differential of V. So this one come in pair. Let's say that's how you write down the integration. Okay. Okay. There's another question about, does the work done by the gas always positive or not? That's a good question. No. Here we go. Let's say if I reverse this process, let's say I'm going backward. I'm going from 4 back to 2. Along this line, I have to tell you exactly how I move back. So I go back here. So everything will look exactly the same, correct? Except now your calculation is going to be 2 minus 4 instead of 4 minus 2. And that is going to be the compression of the gas. And now the work done by the gas is negative. Cool? All right. So the work done can be positive or negative, depends on, does the gas expand or not? If the gas expands, you get positive work done by the gas. If the gas get compressed, then you get negative work done by the gas. Okay. Or it could be 0 if there's no volume change whatsoever. So gas doesn't do anything. Okay. All right. Try this one. You have 3 mole idle gas undergoes a constant pressure expansion. Again, we started out with the constant pressure because the area under the curve is just a rectangle. So it's sort of like easy to do. But later we'll have more challenging problem. All right. But for now, once again, all right, you have constant pressure process. But now the information that's given to you, it's in terms of temperature. The initial and final temperature are given to be 300K and 400K. Find the work done by the gas. Guys, give it a shot. Let's see. All right, guys, try this one. Okay, you have a PV diagram. Let's start from the beginning, start from the top. Work done by the system. Sorry, let me put system over here. It's going to be integral PdV. So far, so good. Very nice. But now the thing is, they undergo a constant pressure expansion, which is fine. That means P is constant. I can pull it out from the integral here. Cool. And that will be V initial, V final, and that's your initial point. That's your final point. So far, so good. Same thing like before. The integral of dV is just V, and you put just the V initial and V final there. So at the end, I'm just redo everything. So just make you sort of like get sick of this. All right. But at the end, you say, but I don't have the information of the P or the V or whatever. I have only information about the temperature. And as you notice, you have the number of mole in here. And here comes the equation of states. It's idle gas. So the good thing about the idle gas is you always be able to reuse PV equal to nRT at all time. And that allow you to do PV final. It's going to be nRT final. You guys with me? Subtract out nRT initial point. Nice. And that's it. nR pretty much constant. So I can pull it out. It's 3 mole. R is R. Just leave it there. We can plug in numbers later. And it's just the T final minus T initial. So what you're looking at this is like, as long as your gas is getting hotter at a constant pressure, your final temperature here is higher than the initial temperature. So that's good. That gives you positive 100K. With me, guys? And once again, the mathematics takes care of the sign right there. The temperature is higher, the change is positive, so the work done is also positive. And that is the area under the curve that we are talking about right here. And everyone expects to be positive work because, of course, it's going from small to bigger volume right there. Positive work done. Done. Okay, cool. So far, so good. Get going to the more challenging question. Try this one, guys. So now the path could be more complex. It's not just like a straight horizontal line anymore. From this example, determine the work done on a fluid. Here we go. Be careful here. Work done on. Okay. All right. And that expands from I to F as indicated in the figure. That's done. Part B, how much work is performed on the fluid if it's compressed? from F back to I along the same path. Okay, you guys want to give it a try? All right, because now we start to get familiar with how we're going to calculate the work. Okay, so what I'm going to show you with this problem is this. Let's say, well, hey guys, I know if I want to get to figure out the work, it must be the area under the curve. You guys with me? All right, just so we won't get confused with the terms of the W that we use, let me call that the area under the curve here is A. Just positive number, just area, A, area is A. So I know going from I to F is an expansion. Okay, you guys with me so far? Is an expansion. So I know part A, W of the system is going to be positive A. You guys with me?
Okay.
Yes, yes, yes. But then this question is asking you the work done on. So this means they are asking you the work done by the external force or whatever external agents or whatever by the environment, whatever. So my answer in part A is going to be negative A. And that is done. You can figure out the area under the curve yourself. Okay. That is fine. But you got what I'm saying over here? Okay, this is good. All right, try part B. For part B, they're doing the same thing, but backward, right? I mean, same path, but you're going from F back to I. So that means the W by the system now is going to be negative because your gas starting from a big volume to a smaller one, gas get compressed. But how much? The magnitude of the work done must still be A, but now it's going to be negative A. And then they still figure out performance, I mean, some force that acting on the gas. So that means you have to pay attention from the perspective of the external force. And that's going to be opposite to the work done by the system. It's going to be positive A. I don't know, this one sort of give you more confusion or not, but that's what it is. Okay, there's a question coming, let me read. But you guys try to understand what I'm doing right now at this point. Okay, that's a question. Oh, okay, why can't we take, there's a question about why cannot we take the absolute value of the W external as an answer for part A? Okay, here we go. So that's a good question. So there's a colleague asking a question about if you take just the A, because we know this A is going to be the absolute value of the work done between I and F. Everyone with me, right? So we know A is A, the area under the curve can be calculated. That's no big deal. But the crucial point of this one is the sign of the work is the most important aspects that we are trying to focus on right now. Because the process that having the gas expand or contract is going to be totally different in terms of the direction of the energy transfer. That's first thing. And second thing is, because every time that we deal with the force, there are always two opposite sides of the force all the time from Newton's third law, right? Action, reaction. So if you do not indicate which force you are talking about, you will always get confused with the sign. So if you would like to take the answer of part A to be just like, I want to answer A, well, so it's 50-50 chance. Or if you say, well, I just want to call this an absolute of A, that is fine. So if the question only asks you about what is the value of the work done during this process, you can say it's A. That's no big deal. But this one is more specific. They are asking you what is the work done on. So when it's a work done on, you look at this one. Gas is expanding. Somebody tried to compress this gas down, but it's losing with me, losing to the gas winning, the gas is expanding out. So let's say I am the external force. I'm trying to compress my gas down, but it turns out the gas is sort of like pushing me backward. It's like gas is expanding in this case, right? In this case, gas is expanding. So gas is winning. So gas is actually performing the positive work. I am losing. That's why I am doing a negative work. Does that make sense now? Okay, so there's always two sides of the story all the times. Depends on you are looking at the system or you are looking at the external force. Cool. All right, but if you don't care about that, they all magnitude. I mean, they're all sharing the same magnitude of the work done, which is A. All right, but once you talk about the directions, then they're always opposites. Okay, that's another question. So that's the work done by the external on the internal system always negative? No. So once again, everything has two directions. So one more time. If gas expand, okay, let me write it down so it's a little bit clearer. So if gas expands, okay, let's go from here, there to here. So in this case, W by the system, okay, let me do this. W by the system is positive. With me? Because gas expands, so gas perform works. In this case, the work done by the external force will be negative. But then you can have an opposite scenario. You can start from a big one. Oops, sorry. You can start from a big one and then everything shrink down here. So in this case, the work done by the system will be negative because it's compressed down. And the work done by the external force will be positive. So the answer will be the work done by the system can be any sign, positive, zero, negative. Work done by the external will be just opposite to that. That's it. Is that a little bit clearer here? Okay, I hope. All right, so far so good. Keep going. All right. Here we go. Let's do this one and then we take this as the final exercise before we take a break. Sounds good? All right, this is, I think, will be the most challenging one of the first half of the lecture here, guys. A sample of ideal gas is expanding to twice its original volume. Okay, the value is given starting from 1 cubic meter to 2 cubic meter along this curve in the PV diagram. The alpha is given. How much work is done on the expanding gas? See, once again, they asking this. How much work is done on? So what they are looking at over here is the W external. You guys with me now? Very good, very good. All right. But for us, all right, let's stick with the system. So what I can do is the W of the system is going to be integral of the PDV. Cool. So far, so good. But now your curve is given to be the parabolic curve, the alpha V square. So I just plug it in. I cannot pull this out. There you go. So far, so good. And you're going to start from the initial volume to the final volume. Nice. All right, now alpha is constant. I can pull it out. The integration of V squared, you get V cubed over 3 from the V initial to V final. All right, so far so good. Nice. All right, alpha is known. All right, don't worry about this one yet. I can turn this one into Pascal. Okay. The volume now, you're going to get cubed. So you're going to do here, 2 cubed minus 1 cubed. They all divided by 3. You guys with me so far? And once again, mathematics takes care of the sign. Everyone can expect that at the end, the W by the system must be positive because gas is expanding from 1 to 2 cubic meter. And that's confirmed from this result. 8 subtract by 1, that's positive 7. So that's what it is. At the end, you still have a positive number anyway. But the problem is asking you to figure out the W external. That's no big deal, Wajan. If you want the W external, just take the negative sign of what you just got right here. And you are done.
Okay.
Cool. All right. So if this works, then that is pretty much the conclusion of how you can calculate the work done, especially in the gas system, with the help of equation of state of the ideal gas. Okay, everything will be nice and cool after this. But I hope you understand more about the sign that is accompanying the work. Okay, so we'll talk more after the break. All right, take 10 here, guys. See you in a bit. Here we go, guys. Okay, so I think this is a crucial slide to understand the thermodynamics now. I am about to talk to you about the first law of thermodynamics at this point. All right. So let's spend some time talking about this. And I think by understanding this one, it will get you a better, some like a background or some sort of like a foundation of what the first law of thermodynamics is supposed to help us understand things. Here we go. So now we use gas. Okay, gas is going to be our sort of like example everywhere. So we have a gas at some temperature here. T is a by. Oh, problem with the microphone again. Haven't done anything. Okay, better. Hello. Hello. So is it the sounds all right? I just actually moving in and out. So maybe it's very fuzzy atmospheres. Oh, okay. That's weird. Let me try again. Haven't done anything actually. Okay, does this help? Now it's better. Oh, that's weird. Okay. It's okay now? Yeah, hello, test, test. Perfect. Oh, weird. I haven't done anything actually. It's just, oh, it's just electronics and IT sometimes just don't understand. Okay, just thank you for that comments. Just let me know if sometimes like sounds just, just go out of the whatever place that it's supposed to be. Okay, here we go. Guys, you have a gas at some initial temperature. Okay, let's say T sub I. And then the thing about this one is the gas is contained in a movable piston, sort of like in a movable, somehow there is a movable piston that you can move up and down. So this means gas can be expanded or contracted, whatever, depends on the action that you put to the gas. Now, look at the bottom of this gas. It turns out it's pretty much make connections or thermal contact with the energy reservoir at this temperature, which is supposed to be the same. All right. So what is the energy reservoir? Whenever you have the word reservoir, I mean, it must be something big, like water reservoir. That's a huge amount of water there. But now this is the reservoir of energy. So that means the energy reservoir, you are having a huge amount of energy that is accessible to you. But then because we have already learned that the way that you can express the amount or the level of energy is through temperature. So because this is a huge energy piece, so it's supposed to be at a fixed temperature. You guys with me? Like for example, right now, let's say Bangkok is at 30 degrees Celsius, for example. So no matter what you do, for example, I can rub my hands, make it like hot. But of course, this amount of heat won't change the temperature of Bangkok. That's impossible. You can burn them. I mean, you can, like burn things up or whatever. It's too big for you to be able to change anything. It's too big for you to change. So that's why every time that the system is in thermal contact with reservoir, it will take the same temperature to it. Okay, because everything we assume that is going to reach the equilibrium anyway. So that means by having the thermal contact with energy reservoir, it also indicates that the gas is already at the same temperature. Cool? So far so good? All right. So think of it this way. Now, because it's a reservoir, if it's a water reservoir, for example, you can dump some water into the reservoir. The level of the water in your reservoir won't change. You can steal some water from the reservoir. I mean, the water level won't change. Same thing over here. It means you can steal some energy from the environment, or you can dump some energy to the reservoir, the environment in this case. It won't be able to change anything. So that's what I'm saying over here is this scenario is trying to express the constant temperature process. You guys with me? Yeah. So that means whatever you're trying to do with the gas will stay at this temperature, won't change. Nothing you can do about it. Okay, because or you can even think like gas is just part of the energy reservoir. It's just like a mini extension from the energy reservoir. You can think of it that way. Okay. All right. So that's what you have. Now, let's say if gas expand. So that means you start from here and then gas push up. So the gas will fill up the space That's used to be just a vacuum, just a blank space before. So gas expands and everything's moved up here. So gas does work. With me? The work done by the gas is positive. Gas does work. Do you think what will happen to the gas? That's the question. Okay, one more time. Just listen to my question one more time. It's kind of like weird. It's like, it sounds like that's not supposed to be any question whatsoever, but it is. Now you have a gas in thermal contact with energy reservoir at temperature T sub I. Now gas expands, let's say twice as big as the original volume, let's say. So gas expands. So gas perform W. The amount of work done by the gas is positive. What happened to this gas? So weird. Question is so weird. You think this can happen? Gas expand itself, having the temperature fixed at one temperature. Is it possible or not? That is the question. Okay, think carefully. All right. If you sort of unlock this sort of like the logic over here, the rest of thermodynamics will be much simpler. Okay, come again. All right. You have a gas at fixed temperature because it's in thermal contact with energy reservoir. Gas expands. So gas doing positive work. What else supposed to happen? All right. I know some of you just like confused. Like, Ajahn, what are you asking? It's like, does the volume change? Yes, the volume increases. Gas expands here. Yeah, it's expand from here all the way to there. Temperature increases. Okay, temperature cannot because gas always in thermal contact with the energy reservoir. So energy won't change. W external decrease, that's always true. All right. So if you say, okay, because gas do positive work, it means the W external will be negative. That's no big deal. That is fine. But what do you think? What else is supposed to happen here? Otherwise, it won't work. Wow.
No.
Seriously. All right. And this is the key, guys. All right. So here is the answer right here. Heat has to flow in. Okay, nobody's sort of like care about that much. So it turns out heat, there must be some heat energy flow. There must be some heat flow into it. Doesn't have to flow in that particular form, but that mean there must be some heat flow into the system, guys. Seriously. All right, so think about this. Okay, so the key is temperature is fixed. So that means internal energy of the gas will not change. Remember internal energy? We talked about this one, like, okay, instead of talking about the total kinetic energy of the gas, it's too long. We're just going to say, hey, this is a constant temperature gas. So when the gas is at constant temperature, it means the energy of the gas will not change. So I will say the internal energy of the gas does not change. The delta is 0. You guys with me now? Okay, with me? All right, there's a question. This is how an AC works. Not yet. All right, we'll get to that, but that's very good connections right there. Almost. This is the sort of like a like maybe it's one step closer to that AC conditions, but very close. Yes, good question. Okay, here we go. So now, because gas, let's say I am the gas. Let's say my temperature is fixed. So it means my energy will be fixed. So that means my energy will not change. Okay?
Okay.
All right. But then I do the work. I am performing the work. I am working. I'm pushing things up. Like, I'm pushing up the ceiling there. Here, I'm doing work. Work is energy transfer. I'm pushing things up, man. So that means I have to spend my energy. There must be some energy of mine that gets spent for me to be able to push up. I mean, I'm probably use my breakfast or whatever, and then I push up. But then the problem of this one is, no, Ajahn. You have to keep your energy fixed. You cannot spend your own energy to push up the ceiling. You guys with me now? How can I do that? I can't if I don't have any helper. I need something else to compensate the work that I'm about to do. Yeah, you have to add more energy to me, and then I'm going to use that additional energy to perform work. And another form of the energy transfer is just heat. So there is a heat flow into me. And it turns out it's balanced out with the work that I just performed. So my energy level stay stationary, stay fixed. My energy in me does not change. Does that make sense now? So what I'm trying to say to you right now is there is the work done. One, there is the change in the internal energy of the gas, and that's the heat. Guys, this
Okay.
first law of thermodynamics is right here. Where does it come from? Does it matter? So there's a question from your friends saying that where does it come from? It comes from the energy reservoir and all this stuff, of course. All right. There is an exchange, but because we assume that the energy reservoir is so big, you can steal some energy from the reservoir, but the reservoir stay fixed in temperature. Yeah. So there's no other way that the energy can flow from. It has to be the energy reservoir. Yes. Okay, cool. At least let's give you an initial sort of like impression of what the first law of thermodynamics is. It's the interplay between these three actors. We have three characters here: work that we just studied, heat that we studied last week, and then our beloved energy of the system. Does it change or not? That's it, guys. This is the interplay between these three characters that will show up in the first law of thermodynamics. All right, before we move on to that, here, look at this example over here on the right. Now I have the same amount of gas, same volume, same initial temperature, but then instead of having this gas in thermal contact with energy reservoir, no, I put it in a container, sealed, insulated. So that means in this particular case, I will not allow any heat to exchange. No. Okay, I will not allow heat to go in or out. That's first thing. Second thing, do you think, is there any work done here? What do you think? Well, of course, Ajahn, look at your slide. You just put it there. All right, no, there's no work because nothing is moving. Okay, even though let's say about, hey guys, let's say membrane just breaks. Just maybe membrane just old and it just, just get separated, it's expired, whatever. Membrane just breaks, gas fill up the whole space, just like in the left case. But even that, no work is being done because you cannot do anything with this. You can put your hands there. You will not feel any gas pushing your hand. So this means there's no work done. There's no evidence of work done by this gas whatsoever. You guys with me? But on the other hand, if you look on the left, if you put your hands here, then you will feel that, hey, the gas pushed my hands up. So the gas performing some work. So over here, no work done. W is also 0. So that means in this particular case, even though the gas expands because membrane just breaks, gas expands from initial volume to the final volume, PV equal to nRT still works and everything. But because you don't have any heat flow, you don't have any work done, delta U will be 0 as well. So that means you are guaranteed that the temperature in this case also fixed. But these two are totally different scenarios. See that? In both cases, delta U does not change. Temperature is a constant. But on the left, you have a lot of activities. There's a work done, there's a heat flow, blah, blah, blah. But on the right, nothing. 0 heat, 0 work. Guarantee that there will be no change in internal energy. But no matter what we do, it's the relationship between these three parameters here. work, heat, and internal energy change. Isn't that cool? All right, and that's, we are going to deal with this under the first law of thermodynamics. But this one just confirm the picture of the path dependence one more time. You cannot talk about just work and heat without saying that how do you bring the system from point A to point B, from point I to point F. You have to tell exactly how you change your system, because W and Q are path dependent. Okay, and then you have to trace the state variables, the change of the gas state. That's always PV equal to nRT. Okay, guys, sounds good.
Okay.
All right. Okay, so let's, okay, there's a question comes in. Okay, let's say I don't understand the first diagram. Okay, the temperature of the gas remain the same because the heat from the gas expansion we've transferred to the hand. Okay. My hand is just okay. My bad. Okay, don't. My hand doesn't have any temperature. Okay, sorry. Let's say let me put a mass on here. Yeah, let me put a mass on here, and then the mass on the left gets elevated. It's like you can use this gas as like an elevator to bring the mass up. So gas can help you lift up the box, for example. But on the right, the box stay there, doesn't change. All right. So that's nothing to do with my hands or this hand. Nothing. This is not in the picture right there. Okay. So yeah, this, I think this is the well, can I say, when you really want to change the state of the gas, you have to do something about it. So this figure over here just showing that there is a hand come in and then pull up the piston. So that's why I allow the gas to expand, something like that. Yeah, so does that make sense? So at the end, what you care about is you just look at how the gas is being changed. Like, for example, in this case, we are focusing on the gas during the expansion, let's say. All right, even though the expansion might come from the hands, pull the piston up, or it could be like you do something with the gas, or gas is about to expand in the first place, and then you just take like a video looking at the expansion of the gas on and on. So, okay, it depends on the real physical stuff that you want to do with it. There are multiple ways that you can do, but what we are focusing on is just the gas, not this hand right here or the mass right here. We're not looking at that. I don't know if this answered the question. Where does the heat added go since temperature remain constant? Okay, one more time. Heat flow in to the gas, but this amount of heat just perfectly fits the amount of work done by the gas. So the gas does not keep any energy to itself. Does that make sense? You steal some energy from the environment, from the reservoir, but then you are doing some work as well. But the amount of energy that transfer in the form of heat, just exactly the same as the amount of work done that you do to expand your volume. So to you, the amount of energy stay fixed, no change. In equal to out. So it's just like you're doing like a balance sheet or something like that. That's, you know, that's an income, and then you have an expense. So the income is perfectly matched with the expense, so you don't have any saving left or something like that, or the amount of savings stay the same. Okay. Yes. Okay. All right. Let's move on a little bit further. It might help. Okay. This start to get sort of like, you know, in a way a little bit. So before we jump into the first law of thermodynamics, the last thing that I want to mention one more time is, all right, this is our third component over here that we would like to officially announce. Welcome internal energy, guys.
Okay.
All right. So it's just the total kinetic energy of the particles in your system. Right? You average them all, you sum them all, you average and everything, you do statistics and everything. So that is it. So it's nothing more than just the total kinetic energy of the gas. Okay, and because we are looking at the ideal gas, you can always calculate that total kinetic energy to be 3/2 nRT all the time.
Okay.
That's it. All right. And just to be perfectly clear, what you are dealing with over here is the monatomic gas. It's a monatomic ideal gas. And because it's monatomic, the kinetic energy is going to be just a translational kinetic energy. And that's why you have 3/2 nRT over here. All right, to derive this expression over here, you need the kinetic theory of gas, and that would take us like maybe 2 more lectures to talk about it. So that would be too much. So just let it go. All right. But the good thing about this one is it still maintain the features of energy. The good thing about energy that we have been using it for so long and we love it so much is because it's path independence, guys. Okay, remember this, the mouse, the object, if I put it up here, one more thing, MGH, I can do zigzag movement. Once I arrive at the final point is MGH. I can throw it to you, you throw it back, and then I put it here, it's MGH. It doesn't care. As long as once you just look at this one, it's right there, everyone will say exactly the same, that the potential energy of this mouse is MGH. The nice thing about energy is it's path independence. Same thing as 1/2 mv squared. You don't have to care how can that mass pick up the velocity v. I don't care. But as long as it has the velocity v, the kinetic energy is 1/2 mv squared. It's path independence. Okay, so that's a nice thing about this one. And it can tell the state of your system. So it's another crucial member to our group that we are going to use it. But the nice thing that set this U apart from the W and Q is this one is path independence. We love them. We love it. We love you. Not you here is you, internal energy here, yeah? Okay, guys. So if you're looking at the ideal gas kinetic energy, which is now we can call it U, is just 3/2 nRT. Works. Okay. All right, here we go. So with that, now we are ready, guys. It's the first law of thermodynamics is in our hand right now. So these are the 3 components in the first law of thermodynamics. Okay. First, heat. No problem, Matan. Yeah. Okay. That's a heat flow. Work is right there. Okay. And that's it. These two is these two are energy transfer. So every time that there are some transfer, it will eventually lead you to the change of the internal energy. And that's it, guys. You are done. So the first law of thermodynamics is nothing more than just the conservation of energy. It's actually, it's what? It's it's like a doing like accounting. You just try to look at the transaction, right? Is there any energy transaction? Is there incoming transaction? Is there outgoing transaction? If there are, then there must be some change of the energy. So you can think of the energy as like a currency or whatever, as like a balance in your statement or whatever. Does that make sense? All right. So the only thing that is confusing to most of the whatever students and the reader of many textbook is the sign. This is annoying. And I don't know how to fix this. If you read at some book will write the first law of thermodynamics like on the left, Q plus W. Some book will write on the right, Q minus W. And it confuses people all the time. Well, why? What kind of law have 2 forms, plus or minus? It looks crucial. The answer is no. The answer is you have to see what the W is. All right, now this is going to be the final point that we want to conclude this. Can you guess what the W in these 2 means based on the W that we have studied before the break? All right, look at this carefully. Look at this carefully, okay? You have the delta U, the change in the temperature, and the Q and the W, right? All right, now it's my time to explain everything. So let me stick with the right expression first, just for now, all right? Because that's going to be the one that we are going to use later. Okay, first, remember the heat, guys. Q, okay, let me use red color here. Heat. We said positive means heat flow into the system. Now I'm going to use it now. This is important. So whenever you have a heat enter the system, that is positive heat. Positive heat means heat is given to the system that's flow in. That's something energy flow into the system, what should be the final effects to the change in the internal energy? Well, of course, then it's going to be positive change to the U. With me, guys? So that means there's a heat flow in. It's going to increase my U, increase my internal energy. On the other hand, if the heat is leaving the system, if the heat is flowing out, my delta is going to be negative. So that means my delta U and Q supposed to have the same sign all the time. Positive Q mean positive direction of the delta U. Does that make sense? Okay, okay. All right, very good. Now look at the W, guys. If the W is the W system, okay. If the W is a system, then when you have a positive W, means system is doing the work. I am the system. If I am doing some work, my energy is supposed to be reduced. With me? Because I have to spend my energy to do that work. So that is why I need the negative sign in front of the W of the system. Because positive work done by the system will have the negative effect on the delta of the internal energy. You guys with me?
Okay.
And that's conclude this expression right here. If you write your first law of thermodynamics as delta U plus one more time, delta U equal to Q minus W, that W must mean W of the system. Okay, okay. And then now next time, if you read the textbook and the textbook write it something like this, delta U equal to Q plus W, now you will be able to tell this is the W external. That's all.
Okay.
That's no big deal. Okay. So it turns out in our case, or I don't know, I made a good decision or not, but to us, because we stick with the system so much, from now on, I'm going to just call the W system to be just the W. And maybe this is a bad decision because the reference text, they use the W to be the W external. So you might have some confusion with, that's it, maybe. But anyway, I already made some sort of like a conclusion that it seemed to be less confusing for you to take the W to be the W of the system. It seems like you made less mistake there. Right? It's also kind of tough for you to think of external work all the time because we are focusing so much on the system. All right, guys. So in conclusion, we are going to stick with this. All right. And let me sort of rewrite everything sort of nicely. So I'm just going to get rid of this, everything. So I hope you understand what this means now. Delta U equal to Q minus W. And your W that you're looking at this point is the W of the system all the time. And that is the first law of thermodynamics, guys.
Okay.
Okay. All right. So it's just an energy transfer combined with the change of the U, that's for sure. So what we are talking here is just the conservation of energy. It's nothing much to it. Okay. All right, guys. So once we know this, let's practice. Okay. But before we get sort of like that practice problems and things, let me ask you a simple, quick question, guys. Okay. Ready? Okay. So just kidding. Ready? If I have a gas and I warm up the gas by maybe lighting the fire or whatever, the temperature of the gas increases. Yes or no? One more time. I have a gas. I just warm that gas up by lighting the fire or whatever at the bottom of the gas container. The temperature of the gas will increase. Yes or no? Okay, that's some no. Okay, some no. Okay. Okay, one more time. Increase by a bit. Yes. Okay, that's some say yes, some say yes. Some say somewhere in between. Sort of like, okay. Okay, everyone seems to agree because it sounds common sense. But John, of course, you have a gas, you warm up. I mean, sort of you burn the gas up, then the temperature of the gas is supposed to be higher. That's temperature rises normal, right? Once you study this first law of thermodynamics, you have to ask me back first. But John, wait a second. Do you allow that gas to expand or not? You guys with me now? Okay, one more time. If I just only say, I just light the fire underneath the gas, it won't be able to tell if the gas is going to get higher in temperature or even lower in temperature. Does that make sense? Because if you allow the gas to expand so much, so fast, so big, then the amount of work done by the gas could be bigger than the amount of heat that I provide to the gas. And eventually the gas might even get cooler. Make sense now? That's the first law of thermodynamics. You have to take into account both sides of the story. Now you have heat and you have mechanical work. So by saying that, just hey, I'm just lighting the fire, so it's mean I provide the gas with some heat, right? That's an energy transfer to the gas. That cannot be sort of like deciding factor that the gas is going to rise in temperature or not. You have to ask or you check. You have to double check. Oh, wait, Dan. Let's check what happens to the physical stuff of the gas. Does the gas expands as well? If the gas expands so much, it could be that you end up with the lower temperature gas. You see what this is trying to get you to now? Or even there could be a special case, say the amount of heat that you give to the gas is perfectly balanced with the amount of work done that the gas is expanding. So these two might just cancel out. Then you still have no change in temperature. It's also possible now. All right. So that is the whole business of the first law of thermodynamics. Heat, work will be the two factors that eventually decide what happens to the change in the internal energy. And that's
Okay.
take home message from me. Okay, guys. Okay, let's take a look at, let's practice. Let's do a basic things now. And this will take everything that you have learned, put it in here. Let's start with just the sign. The drawing shows a pressure volume graph in which a gas expands at constant pressure from A to B, fine, and then go from B to C, constant volume, no problem. Complete the signs in the table below, guys. Woo. Okay, maybe that's annoying. Okay, right, guys, go ahead. Let's go from A to B first. All right. The table already gave you a clue that delta U is positive. What happened to the Q and the W from A to B? Let's attack the easy one first. From A to B, gas expands. W is always positive. With me? Gas expands. Now, from the first law of thermodynamics, delta U equal to Q minus W. Don't forget, from now on, W of us is W of the system. Easy. Gas expands, W is positive, done. So Q is going to be delta U plus W because they're both positive. So of course, this will lead to a positive Q. With me, guys? And that is done from A to B. From B to C, that's easy always because no change in volume. You can put 0 here, right there, right away. And from the first law of thermodynamics, delta U equal to Q minus W. W is gone. Whatever Q is, the delta U will be exactly the same sign because they already gave you that the Q is positive. So delta U must be positive along with it. And you are done. Okay?
Okay.
Cool. All right, maybe this is too easy, but at least this gives you a starting point of what is going on in terms of the sign and the directions of the change. Very important. All right. One important point that you have to make sure that you put this into your consideration all the time, guys. I don't know how much I can stress this enough, is the delta U.
Okay.
Delta U, not the U. Delta U. All right. because Q and W are energy transfer, is a transaction. Okay, so the transaction cannot be equal to the amount of the money in your bank. The transaction will only tell you what will has an effect in the change of your money in the bank. Yeah, I give you 10 baht. I'm not going to be able to tell how much money you're going to have now, but I know that if I give you 10 baht, your balance will be positively changed 10 baht. You see? All right. Delta U is the one that you put in this equation, not the U. Okay. Get going, guys. Here, harder, no more clues, purely asking you to do it yourself now. A diagram shows a pressure versus volume plot for a three-step process. Determine the sign of delta U, the Q, and W, your own, changing from A to B, B to C, C to A. All right, guys. Now it's your turn. No clue, no more. You do it yourself. All right, but we're gonna sort of like mimic that one. So we're gonna have three main character of us here: delta U, Q, and W. Let's attack A to B first. All right, here we go, guys. What should happen between A to B? Between A and B? Let's attack the easy one. Well, Adan, it's expansion from A to B. It's getting bigger in volume, guarantee that the W is gonna be positive. All right. Now the hardest part is here. What else? What else? Now, this one, you already had a clue that delta U is positive, but this one is none. There's nothing here. What can you do next? Here comes the thing. The nice thing about the PV diagram is this. And for those of you that come from chemistry or whatever, I think this will help in your future career. Oh, maybe not that much. Just anyway, the way that you think of the PV diagram. Look at the PV diagram one more time, guys. Every time you have a PV diagram, so let me sort of like draw a big one here for now for you guys. Because we're looking at the gas as our sample system, PV equal to nRT, correct? And we already discussed this briefly that if the gas does not change in quantity, R is always constant. And let's say if you fix your temperature, so it means you make the whole right side of this equation to be just a purely constant. It's just a pure constant here. Okay. So that means you're going to have PV equal to some constant C. But then because you know P is the y-axis, V is the x-axis, you guys remember this curve here? X, Y equal to constant. What kind of shape this curve is? X, Y equal to C. Yeah, some of you probably noticed this. When X is big, Y is small. When Y is big, X is small. So the shape of this curve will look like this. With me? All right. I think it's named like hyperbolic. I don't know. It's like, I don't know. It actually is a hyperbolic curve, but then you turn your axis 45 degrees. Okay. And then you might have this negative side of this one as well. But because we only care about the positive values. And plus, you also know that if the value of the C is bigger, there'll be another line that's higher. If the value of the C growing bigger, that's going to be like that. Yeah. So that's the XY equal to constant curve. So come back to here. Well, Ajahn, you're going from A to B. A must be sitting on some temperature according to PV equal to nRT. So actually, I can overlay this sort of like that constant temperature curve here that A is passing. You guys with me? And point B must be, oh, from the look of it, it's not going to be sharing the same curve here. So point B is supposed to be on another line here that is actually higher. But now, because we know the value of the C related to nRT, so actually this is representing the high temperature. And this is going to be low. You guys with me now? Okay. And C is supposed to be somewhere in between. So let me sort of draw that C. C is supposed to be sitting on another curve right there. Okay, maybe my curve doesn't look so nice, but that's the point. That C is going to be on another curve right there. And let's say T must be somewhere in the middle. T in the middle. There you go. Got that one? Okay. So going from A to B, guys, you jumping from the lower line to a higher line. Actually, this line has a name because it's a line that representing the constant temperature line. This one we'll call isotherm. It's an isothermal curve. So going from A to B, you're jumping from a lower isotherm to a higher isotherm. You're jumping from a low temperature to a higher temperature. But we remember the U for the ideal gas is always 3/2 nRT, guys. You increase in temperature, you increase your internal energy, okay? And that's give you a positive change and you're done. You see? So by the help of the PV diagram, along with the understanding of the equation of states, you know that there is an overlying isotherm in the all of the PV diagram in this world all the time. So I think it seems like it's very useful to always have this in sort of in your visualization of the PV diagram. So going from A to B, you're jumping from a lower isotherm to a higher isotherm. So it's a guarantee that you are increased in temperature. So when the temperature rises, U increases. So the delta U is positive. And once you have done with these two, things is good now because from first law of thermodynamics, delta U equal to Q minus W. So the Q is the delta U plus W. But now those delta U and W are both positive. So it's guaranteed that the Q will be positive as well. See? So actually now you will be able to fill the sign of these pretty much tables by your own. This one sort of give you a clue already with the delta U, but actually if you go back to this example, that has to be the case because you're going from A to B. A must be lying on one isotherm here, and the B must be on another one that is higher, lying higher. So you know, going from A to B, the delta U must be positive because you're jumping from a lower isotherm to a higher one. Cool? Sort of okay. All right, so that's what it is. Let's continue, shall we? All right, let's go from B to C, guys. B to C, attack the easy one first. B to C, you're still expanding. The gas is growing bigger. So it's still positive work done by the gas. That's done. But now you know better now because jumping from B to C, you jumping off from a higher isotherm to a lower one. So the delta U guaranteed to be negative because you lower the temperature. Yes. And now the Q is going to be tough a little bit because Q is just the sum of the two. So you don't know exactly how would that end up. It could be zero, whatever. So let's put question mark here because we need some numerical calculation and everything. But for now, right, this is good enough. Okay, cool. All right, let's go from C back to A. Right, coming from C back to A, one thing that you know right away is you are compressing the gas. The volume is down. So you are guaranteed that you're going to get a negative work done by the gas. Second thing is you're jumping from C to A, you're jumping from a higher isotherm, it's the T in the middle, down to the T temperature at the low point. So you are guaranteed that you're going to get a negative change in your internal energy. And Q equal to delta U plus W because now the delta U and the W both negative. So you're guaranteed that you're going to get a negative heat flow. Cool. All right. So just make a quick summary on what we are doing over here is, as you can see, we use PV diagram. We use PV equal to nRT. We use first law of thermodynamics here. Plus, if you would like to be careful with the sign, see this one? A to B, Q is positive. What does it mean? It means during this process from A to B, there is a heat flow into the gas. So from A to B, gas is expanding. There is a heat flow into the gas. At the end of this process, the energy of the gas is higher because you have a positive change of the internal energy. See, this is a whole thing that you can make the analysis of what is going on with the gas. All right. And this kind of analysis will sort of keep growing and growing with numerical calculations and the processes that we are about to discuss later. Okay, cool. I don't know, does that give you like a good enough picture of what is going on with the first law of thermodynamics here? All right, try one more time, guys. Last problems of the day. All right. But I hope having this in your hands will help what is going on is about to going next time, right? Because we're going to do more and more calculation here. Okay. A system undergoes a cyclic process as shown. So the cyclic process is just the process that come back to the original position, full circle there. Find the change in internal energy at the end of each cycle. So they want to know what is the delta U after you already complete one cycle. B, what about the total work done? C, what about the heat transfer into the system? This is still a simple one because they just want to know what happens after the whole cycle. Okay. Later, next time, we're going to do a fine detailed calculation on each segment, A to B, B to C, C to D, D back to A. We can do that now, but I think that would take some time. But for now, let's look at the big picture here. You guys, please answer part A for me. This is annoying. What is the change in the internal energy at the end of each cycle, guys? A to B, B to C, C to D, and then back to A. Yes? Yes? A to B, B to C, C to D, back to A. What is the change in the internal energy, guys? Very good, very good, very good. Yes. Be confident. Yes. 0. Thank you. Perfect.
Okay.
Very nice. Okay, everyone else seems to agree? Yes, because you come back to the original position is the energy. Energy, you start here, you go all the way around the world, you come back here, no energy change. It's right there. You're done. Nice. Okay, part B. What about the total work done in one cycle? All right, so now this one is not bad too, Ajahn. That's kind of nice. Going from A to B, the work done is going to be the area under the curve, right? So what I can do is just figure out the area under the curve here. There you go. That's from A to B. I can get that. A to B. Okay. Oh, this is kind of fun over here. There you go. All right. So that's from A to B. This yellow area here will give you the work done. And everyone knows going from A to B is going to be a positive change. So this is going to give you the positive work done. Yellow is positive. Let me mark on here. That's a positive. B to C, no work. Now C back to D, you're going to get the area under the curve as well. Yeah. But this one is going to give you a negative value of this area. You guys with me? We practiced that this already in the first half of this lecture. So seems like all you have left is just going to be just the area that is enclosed by this path over here, because going from D back to A won't give you any work done, no volume change. So at the end, the work done that you do for a complete cycle is just the area that enclosed by this one. With me? Yeah. And it's looked to be net positive because the yellow shaded area is positive, and then the blue one is just negative. So you just erase the bottom half of the bottom portion of this area. So you are left with just a big chunk of positive area there. So at the end, the W for the whole cycle is going to be just the width times the height right there. So it's going to be P1 minus P2 multiplied by V2 minus V1. You guys with me? And you're guaranteed this is going to be positive because, I mean, just by using the arguments that we just did, it's going to be positive work done. So at the end of the cycle, the gas perform net positive work. And now down to the part C, guys. What about the heat transfer into the system? Oh, no problem, Ajahn. First law of thermodynamics. Delta U equal to Q minus W. So the Q is just delta U plus W. That's no delta U. Whatever the W is, the Q must be it. And that's it. So it's the same thing as part B. And you are done.
Okay.
That's it, guys, for today. Sounds good? Yeah. Not too bad. See, so the first law of thermodynamics is kind of like all right, except it's annoyingly detailed. There's so many pieces that you have to take care of. You have to use equation of state. You have to look at the PV diagram. You have to look at the curve. You have to, take care of this. Each one you have to do. But at the end, the grand understanding of the first law of thermodynamics is just conservation of energy through heat and work. Done. Thank you, guys.
Okay.
Any questions? Okay. If y delta u is 0. Oh, okay. So the delta u is 0 because you come back to the original position. The energy is path independent. So when they are path independent, means if you're standing at the same position, you have the same energy all the time. Does that make sense? Okay. All right. Just like what I say over here. If this is the mass, I pull it up. Okay. The mass has like no initial gravitational energy. There's no kinetic energy. I can do anything with this mass. And once I put it back here, and you just take a look at this one more time, you say, Ajahn, same energy, even though it might have gone through so much. But once it's here, same state of this, same height, same velocity, it has the same amount of energy. Same thing with the gas. You can start from A, and then you can do anything with the gas, but then eventually you come back to point A. So when you take a look at it, you say, you must have the same energy. So the delta must be 0 because your energy does not change at all. Okay, cool. All right. Yeah, the homework's due 30 January. I think that's far enough, I think. All right. Yeah, part B. Okay. Part B, one more time. So when you look at this one, you're going from A to B, right? From A to B, what you have here is the work done from A to B is the area under the curve. So I think we can erase this and start this one more time. So going from A to B, you are doing the work equal to the area under the curve. So this is A to B. So this is going to be your area under the curve. All right. Okay. I can write down in detail over here that work done from A to B is going to be the whole height here, P1, multiplied by the volume change, the one that we just did earlier before the break, V2 minus V1. With me, guys? Okay, so that is the work done from A to B. B to C, no work done. So W from B to C is 0. Now W from C to D is the bottom part over here. And if I do it perfectly, it's going to be P2 now. And then final minus initial is going to be V1 minus V2. Okay. All right. And then D2A is 0 again. So the total work for the whole cycle is just going to be the sum of these 4 terms. And as you can see, it's just like you taking the P1 V2 minus V1, and then you you add P2 V1 minus V2. There you go. All right. And at the end, it's the same thing as you take the yellow area, subtract out the red shaded area there. So you ended up with just the area that's inside this one. Once you combine these two together. Does that help? So it's just like going from A to B, you do positive work, but then you do a little bit of negative work from C back to D. So you erase part of your positive work a little bit, but you still have the leftover to be net positive work done. Okay, cool. Where can we find the homework is already in the Google Classroom in the classwork material, I think. All right. So the homework is linked to the assignment number 1. So I try to make them correspond to each other. So you have a submission form that we already agreed that all you need to do is just submit something. I only ask you for some problems in the homework anyway. So, all right, just make sure that you check them out. Okay. All right, cool. Everything will be on the Google Classroom. Yeah, just check that area there and you can download the PDF form. All right, guys, any other questions? All right. Yeah, it looks good. Okay. If not, then thank you very much. And I will see you guys on Wednesday. Bye-bye. Thank you. Okay. Bye-bye. Take care, guys.